We have one final piece to discuss for electrophilic addition reactions. We've already talked about how the reaction occurs, the mechanism. It forms a carbocation intermediate, and the stability of the two possible carbocation intermediates gives rise to the product that we see. And we see one product favored over the other. So the reaction proceeds with regioselectivity, or Markovnikov selectivity. This occurs with the X adding to the more substituted carbon and the hydrogen adding to the less substituted carbon. We haven't yet talked about the stereochemistry of these reactions. These reactions do not proceed with stereoselectivity, meaning that when more than one stereoisomer can form in these reactions, they will both form. And in an electrophilic addition reaction, we sometimes have the possibility to form two different stereoisomers of the product. As an example, let's start with an alkene in which we already have some stereochemistry defined. In this substrate, there's already a difference between the top and bottom faces of the alkene due to the OH group. So we know that the reaction will proceed to give us regioselectivity, that the bromine will end up on the more substituted carbon. But we don't know if it will be on the same face as the OH or the opposite face. And because these reactions do not proceed stereoselectively, we will get a mixture of the two stereoisomeric products. And that's because the reaction proceeds through a carbocation intermediate. So in more detail, the alkene will attack the hydrogen of the HBr bond, and the HBr bond will break and the electrons will go to the bromine. This forms a carbocation intermediate. And we have to remember that the carbocation intermediate is planar. And the cation is associated with a p orbital that sits above and below the plane of the carbocation. With this empty p orbital sitting above and below the plane, this means that bromine or bromide can now attack on the top face or the bottom face. When it attacks from the top face, the bromine will be pointing up or will be on the same side as the OH group. And when it attacks from the bottom face, the bromine will be pointing back or on the opposite side as the OH group. The two products that we form then have one stereocenter that's the same and the other stereocenter is inverted. So these two products are diastereomers. Okay, so because there is a carbocation intermediate, the reaction will form both possible stereoisomers of the product. And now let's look at the case where we don't have a chiral carbon in our starting material, but we do have an alkene with two different groups on the carbon. This reaction follows the same mechanistic steps to form the product with the bromine on the more substituted carbon and the hydrogen on the less substituted carbon. The reaction begins with the alkene attacking the hydrogen of HBr to form the carbocation intermediate. Once again, that carbocation intermediate can be attacked from the top face or the bottom face. And here, attack on the top face gives the product we'll draw in red, it will have the bromine pointing up or towards us. An attack at the bottom face gives us the product that we'll draw in blue, and it will have the bromine pointing back or away from us. And now in this case, because we only have one chiral carbon, the two products that we form are enantiomers. Let's do a concept check here. Draw all isomers formed in the reaction shown. We'll follow the same reaction steps. The alkene attacks the hydrogen, and the HBr bond breaks to form a carbocation and bromide anion. In this example, there are two possible regioisomers for the carbocation intermediate, so we need to be sure to draw both. Then for each carbocation, the nucleophilic bromide can attack from the top or the bottom face, giving two enantiomers of the product. For the second regioisomer, the bromide can also attack from the top or bottom face. And in this case, the two products drawn are the same. So overall, there are three isomers of the product that form in this reaction.